Welcome to Group G2T2's video on RSA algorithm for CS104, presented by Jingzhi, Mingyan, Ryan, and I, Shenqin. To begin, there will be 4 parts to this video, starting with an introduction to RSA, followed by an illustration of RSA in action with the help of Alice and Bob. We will also go through the mathematical proof of RSA, and lastly, the application and implication of RSA in real life. So, let us begin. What is RSA? RSA, or commonly known as Rivet Shamir Edelman, is a form of asymmetrical encryption, which uses 2 keys for encryption, namely a public and private key pair. Once the data is encrypted with the public key, it can only be decrypted by the private key. Let's say we have a digital document, a document file, for example. I need a way to show that the digital document is approved and made by me, not altered by anyone else. Since it's a digital document, anyone can copy and say it's their own work. We need a way to guarantee the authorship of the document. Also, anyone can send a copy to you. We need a way to guarantee that the document is sent from a trustworthy source. Lastly, someone might also edit the document without permission and pass it off as the original. We need a way to show that the document has not been altered during transmission. Therefore, using this RSA encryption, we are able to ensure the non-repudiation, the authorization, and the integrity of the document file. Moving on to the understanding of RSA, let's understand RSA with the help of Alice and Bob. Alice, the sender, wants to send a confidential number to Bob, who is the recipient. Using RSA cryptography to encrypt her data, Alice requires Bob's public key to encrypt her data, which is, as seen on the left, the blue key. Bob would thus also have to generate his private key later to de-encrypt the data. Firstly, Bob generates his RSA keys by selecting 2 primes, P and Q. P equals to 23, Q equals to 41. But keep in mind that in the real world, P and Q will be much larger prime numbers. Bob multiplies P and Q together to get the modulus n, where n equals to 943. 943 is one part of the public key which Bob tells Alice and to the rest of the world if he wishes. Next, Bob chooses another number e, which must be a relative prime to p minus 1 times q minus 1. In this case, p minus 1 times q minus 1 equals to 880. So, we will just pick the number 7 for the simplicity's sake. Therefore, Bob's public key consists of e, which is 7, and n, which is 943. Now, Alice knows enough to encode a message to Bob. Supposedly, for this example, the message that Alice wished to send to Bob would be the number 35, as represented by M. Using Bob's public key, consisting of E and N, Alice calculates the value of the ciphertext C, using the equation M to the power of E mod N. The number 545 is the ciphertext that Alice sends to Bob. Bob receives the ciphertext C, which is 545, from Alice. However, in order to decode the ciphertext, Bob has to generate his private key, which is missing the component D. Ryan will be talking about how Bob derives the value of D and hence the original message.
For Bob to decode the ciphertext, which is 545 in this case, he has to solve for a value D such that it satisfies the first equation below, which is ED congruent to 1 mod P minus 1 times Q minus 1. In this scenario, a value D which satisfies the equation would be where D equals to 503. Since 7 times 503 gives you 3521, and 3521 equals 4 times 880 plus 1. Therefore, 7 times 503 is congruent to 1 mod 880. Therefore, Bob's private key is made up of D and N, where D equals to 503 and N equals to 943. To find out the message, Bob has to solve for the equation C to the power of D mod N, where C is the ciphertext, D is the value calculated earlier, N is the RSA modulus. This might look like a horrible calculation to work on. However, notice that 503 can be expressed as 256 plus 128 plus 64 plus 32 plus 16 plus 4 plus 2 plus 1, which is the binary expansion of 503. Using the laws of exponents, we will be able to reach the last equation. Since our goal is to find the value of 545 to the power of 503 mod 943, we can calculate all the parts of the product mod 943. By repeated squaring of 545, we can then get all the exponents that are powers of 2, and we will finally obtain the following table of results as shown below. Bob will be able to decode the ciphertext using this slightly tedious calculation, but is easy for a computer to do so. Using the table of results calculated earlier, Bob will be able to obtain the original message of 35.
In summary, the message M, which is 35, is encoded by the public key using the formula M to the power of E mod N. We will then get the ciphertext C, which is 545. Thereafter, the ciphertext is decoded by the private key using the formula C to the power of D mod N. These are the summary of the steps of RSA in short, as shown on the slide. You can pause here to take a look at it. Moving on, Qingzi will be talking about the proof of correctness of RSA.
Euler's theorem states that if n and a are co-prime positive integers, then a raised to the power of totient of n is congruent to 1. And the totient are integers k, where k is more than 1 and less than n, for which the greatest common divisor between them is 1. So let's start with the proposition. When ed is congruent to 1 mod phi n, n equals to pq are prime, ed are positive integers, and the greatest common divisor between m and n is 1. For a message n, if I encrypt and decrypt, I should get the same m back. So for now, let's look at ed. ed can be written as 1 mod phi n, and we can rewrite this into phi n x plus 1 for some integer x. So now let's look at encryption. To encrypt, we take the message m to the power of the e mod n to get c, where e is the public key and c is the ciphertext. To decrypt, we take the ciphertext C to the power of the private key mod n, and we get M. Now we need to prove that if I encrypt M with E and then decrypt with D, I should get back the same M. To do this, we can write M to the power of E mod n or D, where M to the power of E mod n is the ciphertext, mod n equals to M, the original message. We can rewrite this as M to the power of ED using the modular exponentation rule. And based on ED that we've rewritten just now, we can rewrite m to the power of ed mod n as m to the power of phi n x plus 1 mod n. Now let's take out the plus 1. It becomes m to the power of 1 times m to the power of phi n x mod n. Let's apply Euler's theorem. Where a to the power of phi n is equivalent to 1 mod n. And since m and n have the greatest common divisor of 1, we can use Euler's theorem here. So m to the power 1 times m to the power of phi n x mod n is equivalent to m to the power 1 times 1 to the power of x mod n. Since m to the power of 1 is m and 1 to the power of x is 1, we get m. And therefore, we prove the correctness of RSA, and RSA is now legit.
Moving on from the proof of correctness, we will now be talking about the applications and implications of RSA. So there are some notable applications. Firstly, we have the certification authority known as CA. So there are some examples of trusted CAs, which includes Commodore and GeoTrust. Okay, next up we have the key exchange. So in RSA, key exchange has normally been seen in the key exchange part of the transport layer security, also known as TLS. However, in the latest version of TLS 1.3, RSA has now been removed. And next we'll be talking about the key-based authentication. So a key pair can be generated and the public key is then placed onto the remote server it wishes to access. The possession of the private key will serve as their authentication. This can be seen in the secure shell or SSH authentication protocol. Next, we'll talk about some notable uses of RSA. So RSA algorithm is used to digitally sign documents. A simple example for this would be the Adobe Acrobat Reader DC applications, where owners can digitally sign on their PDFs to prevent further editing from any other users or readers. RSA is also used to secure connections between VPN servers and clients. Under protocols like OpenVPN, TLS handshakes can use the RSA algorithm to exchange keys and establish a secure channel. However, this has been removed as of TLS 1.3. Now I'll be talking about the implications of RSA. So firstly, the public and private keys are related mathematically. However, the parameters are chosen so that the calculating the private key from the public key is either impossible, takes an absurd amount of time, or is prohibitively expensive. A cryptographically secure pseudo-random number generator, or RNG, which has been properly seeded with adequate entropy, is mandatory to generate the primes P and Q. Why so? If you use small prime numbers or primes that are too close in value to each other, like the example shown, it allows the key to be decrypted easily. Furthermore, for the RSA encryption to be effective, a key of at least 1024 bits should be used. However, to improve the confidence of RSA, users are highly encouraged to use keys of either 2048 bits or 4096 bits. If the same clear text message is sent to E or more recipients in an encrypted way, and the receiver share the same exponent E, but with different primes P and Q, and therefore N, then it is easy to decrypt the original clear text message via the Chinese remainder theorem. And for a quick fun fact, for nearly 40 years, RSA has stood the test of countless attacks, making it the algorithm of choice for encrypting internet credit card transactions, securing emails, and authenticating phone calls, to name a few.